My G's, my dogs, my homies. Today I'll be going over some ideas that will help you better think like a scientist during your GCSE science exams. But wait, what is science? If you say,
that's when man's tried to understand, explain and predict things, innit?
Then you concede that zodiac signs and palm reading are sciences as well.
Cool, fam.
You may very well interject.
Science is when man runs experiments with chemicals and that.
But if that is the case, then something like astronomy, when you mainly make observations, isn't science. For your GCSEs, let's just settle on using falsifiable observations and experiments to systematically study the structure and behavior of the natural world.
Nah, allow that.
No. Hear me out. I'll break it down, yeah? Structure, how things look, what they're made from. Behavior, how they act, interact, what they tend to do. Natural world, the observable universe, things we can run experiments on and that. Systematically, this just means that it's logical, it follows a theory. Jam, I swear, I'll expand on that later, yeah? Falsifiable. This means it can be shown to be wrong. Basically, you can run an experiment on it to see if the idea is true or false. Falsifiable. We good, yeah? In a future video, what I'll do is that I'll go through the scientific method using the required practicals that you have to learn. But in today's lesson, we'll just be covering these 6 areas. What is a scientific theory? Hypotheses and variables, and I'll also touch on fair test there. Tables and graphs, we'll also talk about reproducibility. Gradients and tangents, and we'll look at anonymous results there. How to describe and explain graphs. And lastly, your physics equations. Today's present is a booklet of command words with several examples and mark schemes showing you how you should format your answers, so check the description at the end of the video for that. I'll also show you how I printed mine off later on, so just stick around for that, okay? What is a scientific theory? When you talk about science, it's never just a theory. No. Different social groups and communities have words in common that mean completely different things. Like when the man them say bare, we don't mean the adjective not clothed or basic, that's bare. We mean the determiner, a large number of. Bare. Same goes for theory. In everyday language, it means a guess, but in science, it's so much more than that, my G. A theory is the best or one of the best explanations that can be made from a group of results. Like Ned Stark, he realized something spooky about them Lannisters. He noticed that parents that have brown hair, even if one of them has blonde hair, are unlikely to give birth to a child with blonde hair. But it's genetic theory that gives an explanation to that consistent observation.
But Uncle Jegz, didn't scientists used to think that the earth was flat and that the sun went around the earth? How do we know that these modern theories aren't wrong as well?
That's a fantastic question. We don't know. We can't know. Science is the movement from ignorance towards objective reality. We are limited by our imagination, senses, and technology. When a genius arises that can think outside of the box, or a technology is developed that can take our senses further into the secrets of nature, then we adapt our theories. This isn't a weakness of science, it's actually its strength. That means science isn't frozen in the norms and the traditions of a particular snapshot of society. Science evolves. When we run good experiments and observations, We are essentially asking Mother Nature a question. The results of the experiments and observation is our answer. But just like your GCSE English literature, the answer is up for various interpretations. For example, man like Hubble discovered that there were other galaxies beyond our own. And when he began making detailed observations, he found that the galaxies were actually moving away from one another. The universe is expanding.
Mother Nature's getting thick, yeah?
Now, there were two competing interpretations of this: the steady state theory and the Big Bang theory. Note that they didn't dispute the results and the observation that the universe is getting larger, but they disputed the mechanism of that expansion. Further experiments proved that the Big Bang theory was the closest thing to reality. To save this video from becoming like an hour long, I'll save the full breakdown of the Big Bang theory and other theories in a later series. Hypotheses and variables. When scientists do experiments, the things that they can change are called variables, and you have three types of them. Dependent, that's what you measure. Independent, that's what you change. Control, that is what you keep the same. Remember DMI for now, okay? Just keep that at the back of your mind. Let's apply this to an experiment. If you've got weed growing in your garden,
Yes, sir. Rastafari.
weed, not weed, weed as in pond weed that you experiment. Look, it's in the syllabus, in your photosynthesis practical. Look, hey, kids, do not do drugs unless it's medicinal. Alright then. The statement that you test out is called your hypothesis, and it should always have your independent and dependent variables stated. An example of an hypothesis is increasing the light intensity increases the rate of photosynthesis of the pondweed. Look at the statement again and try and work out what we're measuring and what we're changing. We are changing the light intensity, so that's our independent variable. We are measuring the rate of photosynthesis, so that's our dependent variable. The control variables are the things that you can also change that can affect the rate of photosynthesis. The three main things that can affect photosynthesis are light, what we're changing, our independent variable, but you also have carbon dioxide and temperature. This now moves on to the idea of fair tests. This is when you only change one variable, you're only changing your independent variable. This means that any change that you measure is due to that one thing you're changing. Bare students say that repeating your results gives you a fair test. We'll repeat results to see if they're reproducible, if our results are reproducible, and to identify any anonymous results. And of course, you run your experiment and collect your results in your results table. Tables and graphs. When you see a results table, what you change usually goes on the left-hand side. Remember, that's your independent variable. Therefore, the dependent variable goes on the right-hand side. In terms of units, never put them below your heading. It should always be in your headings, alright? For the photosynthesis hypothesis, a cheap way of changing the light intensity is to just move the lamp away from the plant. So distance of the lamp goes on the left-hand side. To measure the rate of photosynthesis, we count the number of bubbles coming off the plant in 1 minute. That goes on the right. Here are some typical results. If the examiners really want to check you know the things, they may give you a table that has multiple repeats. They will usually do this so that you can calculate the mean or to identify an anomalous result. You need to be confident on spotting these anomalies. In this example, for each distance, I'll compare each test for any major differences. Looking through this example, you should clock one anomaly here. When we spot anomalies on our tables, we do not include it when we calculate our mean. When I go through the results for each distance, on 40 centimeters I see 3, 3 and then 8. That's just bait. Check what I do. 10 plus 11 plus 10 gives us 31. Divide that by 3, that gives us 10.3. But since my values are whole numbers, I'll round my numbers up or down to get my mean. I do this for 20 centimeters and 30 centimeters. At 40 centimeters, you should have clocked that what we do is to add the 3 and 3 and then we divide by 2. These numbers are simple, so we know the answer should be 3. But look what happens when I put the whole operation in my calculator. I get 4.5. What is this nonsensicals? It divided 3 by 2 first and then added the other 3. Make sure you always press the equals when you sum up your repeats, and only then do you divide the sum to get your mean. When it's time to draw your graph, we have to decide if we're using a bar chart or a line graph.
I hate this bit.
When you clock it, it's actually light work. We have to see if our variable is categoric or continuous.
What?
No, don't stop. Oh man, I lost her.
Tatiana doesn't know everything.
Jaden, first warning.
What did I do?
Hey, Tatiana? It's not that hard. Hey, if you're able to do this, I'll buy you Nando's.
Uncle, do I get Nando's?
Close your lips. Okay, Tatiana, what does categoric sound like?
Categories?
Exactly. If you can put your data into categories, then it's categoric. Categoric variables have values that can be labels. So that's like names of plants or types of material. Now, what does continuous sound like?
Continuous?
Exactly, yes, that's good. If your variable is a number that can be any value, then we call that continuous. Continuous variables can have values called quantities that can be given in magnitudes either by counting, so if you're counting the number of stars, or by measurement, so like light intensity or flow rate, etc. We put categoric data in bar charts and continuous data goes on line graphs. Both of our variables are measurements and not labels, so we need to draw a line graph. Cool, yeah? What I'm gonna do now is show you how to draw the two types of line graphs. I suggest that you practice along with me. You don't get better just by observing. If that were the case, then you can just watch someone playing the piano and then you'll be able to play yourself. Here are the steps I follow when I draw a graph. Number 1, I identify the highest values in both of my variables. Number 2, I extend my axes to be slightly larger than my values. Number 3, I label my axes. Number 4, I make sure the spaces between my scale is equally spaced out. Number 5, I plot the results, and number 6, then I draw my line of best fit. Do you remember DMI that I told you to remember? That stands for dependent measured y-axis. That means that the mean bubbles produced, which was what we measured, will go on the y-axis. I remember the y-axis as the one that's reaching out to grab something upwards, just like a hand, so y-axis. And from DMI, I can work out that my x-axis has to be what I change, which in this case is the distance of the lamp. The highest distance is 50 centimeters and the highest mean number of bubbles is 11. Therefore, I'll extend my y-axis to 12 and my x-axis to 60 and label my axes. A quick side note on how to decide the increments that you go up in. You want to either use 1, 2 or 5 with your decimal point in the correct area. So you could go up in 1s or 0.1 or 1000. But if 5 is better suited for your graph, you could go up in 5s, 0.05, 500 You get that, yeah? Some of my students have used some exotic numbers like 3 and 7s. Nah, we don't do them things. The most appropriate for my y-axis in this case will be 2, and for my x-axis it will be 10. Now make sure each increment is evenly spaced out. Use the guidelines that are given to you, don't try and be fancy. The only A3 line paper I could find didn't have the thicker guidelines, but yours will, so stick to them. Now just plot your results. In science, you have 2 types of lines of best fit that you can decide from based on what your plots are looking like. I know your maths line of best fits are slightly different, but then again, we don't do them things. The way you can tell what you should use is if your plots look like a curve or if they look like they're straight. You probably will always have one plot that doesn't fit your pattern. For straight lines of best fit, don't you dare connect the points together. The whole point, no pun, is to get a general relationship from the sum of all your results. This is clearly a straight line, so we do our line of best fit using a ruler. And you notice this obvious antisocial point here, we circle them out because that's the anomaly. If the points in your graph look like this instead, then dash your ruler to the side, crack your knuckles, and then work them curves. We have to draw these freehands, and ideally in one go. Blam. Gradients and tangents. Okay, we are gonna do a bit more maths now. Jaden.
Huh?
Can you remember what a gradient is?
It's that triangle thing, innit? On the graph.
Most commonly found in the rates of reactions unit in chemistry 2 is the concept of gradients and tangents. We basically need to understand 2 parts of a right angle triangle. The bottom bit is known as the base, and the bit that goes up is called the height. The gradient is the height of the triangle divided by the base. When you plot your graph, we can assign the base and height to the 2 different axes. The height, which is going up, is your y-axis. The base lying flat is your x-axis. Therefore, your gradient is your y-axis divided by your x-axis. The gradient in this example is a measure of how quickly the reaction goes, the rate of reaction. Check how I applied this to a typical example. For the rate of reaction, time is usually on your x-axis. The volume or amount of reactants/product goes on your y-axis. Plotting my results, I clock that it's a straight line, so I get my ruler to draw a straight line of best fit. But this line is special. When you get a line like this, you may be asked, what relationship does this show? You need to say directly proportional. And for 2 reasons. Number 1 is a straight line, and number 2, the line passes through 0, 0 on the bottom left hand corner. The 0, 0 point is also called your origin. You've probably clocked that we can draw a triangle by drawing a line from our line of best fit all the way down to the bottom. When we do that, we measure how big the height is and divide it by how big the base is. Question: what is the rate of reaction at 40 seconds? What we do is that we go up to 40 seconds on our x-axis, since that is the time axis, go up to where that is on our line of best fit. The top of our height here in this example is 40 centimeters cubed. The bottom of the height is 0 centimeters cubed, so 40 take away 0 gives us a total height of our triangle as 40. We do the same for our base and we get 40 seconds. Height divided by base, y divided by x. The rate of reaction at 40 seconds is 40 centimeters cubed divided by 40 seconds, which gives us 1 centimeters cubed per second. The per bit just means that the centimeters cubed was over the seconds in our calculation. It's almost like the divide sign in itself. Sorted.
But uncle, we had a question when the line of best fit wasn't straight. We use a tangent for them things, innit?
Good point, Jaden.
Can my name come off the board now?
No. Look at this next example. Clearly this is not a straight line of best fit, so dash your ruler to the side. Freehand your curve in pencil. I'm only doing it in pen so you can better see it. So yeah, how do we get a triangle from this mess? Watch me do the things. Question: what is the rate of reaction at 40 seconds? A tangent is a straight line that skims across your line of best fit without cutting through it. Now we can draw our triangle. Key things: notice that the triangle does not touch the bottom of our graph. That's why it's always important to take the difference between the top and bottom. Now apply this to my graph and make a small dot where 40 seconds is on my curve of best fit and draw a tangent. The top of the height is 35 centimeters cubed. The bottom is 10 centimeters cubed, which gives us 25 centimeters cubed for my height, the y-axis. The base is 40 seconds again, and dividing the two, that gives us 0.625 centimeters cubed per second. Describing and explaining graphs. Look at this graph. You may be asked to describe and then explain this. A description is just stating what the graph shows. An explanation is stating why the trend is the way it is. If this was a description question, a describe question, they could very well make it a 2-mark question. Most students easily get the first mark. As the concentration of CO2 increases, the rate of photosynthesis increases. The second mark comes from the change to that statement. It doesn't just keep going up, so we also say, after 0.07% CO2, there is no increase in the rate of photosynthesis. A safe bet would be to always use numbers in your graph to add to your answer. An explanation gives reasons for each of your description. CO2 is the raw material needed for photosynthesis to make glucose. This explains why more CO2 will lead to more photosynthesis. Above 0.07% CO2, there are other limiting factors like light and temperature limiting the rate of photosynthesis. This explains why it stops increasing. Now let's try this example. Describe. The mass of sulfur dioxide decreases over time and levels off at around 2009. Explanation. People use cleaner fuels. People are more aware of the dangers caused by sulfur dioxide. Again, the description is what we see in the graph and the explanation is why it is happening. The physics equations. Now for the physics equations. I was going mad trying to work out the best way to get you to understand this. I first placed all the different parts of each equation on the spreadsheet and looked at the frequency of each to try and determine the best way to eat all of it. But I found this YouTube channel called Gorilla Physics. Make sure you check him out. My guy has over 500 videos. The one I'm shouting out is called The Best Way to Memorize Equations for GCSE Physics. I'm a pretty competitive guy, but I give credit where credit is due, and this book that he wrote is amazing. All the details are in the description of his videos, so subscribe to him and check that out. Okay, let me cut this video now, it's getting bare long. So as promised, here is how I printed out the command words booklet. If you don't have a printer, get your teacher to print it off for you and into a booklet like this. The more you familiarize yourself with the format of the command words, the easier your exams become. Make sure you get that, yeah? Free of course. And if you haven't got the adapted syllabus or the revision timetable template from my previous videos, make sure you check those out. You can download them at the description of each video. Like if you like, subscribe if this is something you want to see more of, and yeah, peace.